Thank you all for coming. I'm Troy Runke. I serve as a chairperson for the Madison Steering Committee for the Dairy Innovation Hub. I'm also a professor and a chair of biological systems engineering. You can tell from my shirt that I also work part-time at Target. No, I'm just kidding about that. I grew up on a dairy farm. I consider myself a farmer, though I don't have to get up quite as early anymore. So that's a good thing. Talking a little bit about the session, we're going to have 3 speakers. Each are going to give a 25-minute or so talk. We're going to hold questions and for all 3 of them at the end. So we'll have about a half an hour for questions, both online. If you're online, if you could just type a Q in and then your question. If it's a comment, you can comment or thank the speakers, but to let us know that it's a question that we should be asking, make sure you put that Q in. Nikki will be reading out those questions during the question and answer session at the end. Just a real quick comment on sort of what the Madison Steering Committee does for the Dairy Innovation Hub, as long as I have your attention. Each campus gets a certain amount of funds, and we have, of course, policies and procedures. We have the 4 areas that we've been talking about, and our steering committee is made up of experts on campus from all 4 of those areas. And what we do is we set sort of the processes for looking for those 100 and some projects. How is the money invested? Because it is generous to have the money to do this amazing research, and we have to be very responsible for it. And the steering committee helps steer to make sure those investments are into things that will best serve the community that the money is intended, the dairy industry. So enough of sort of my soapbox. I want to introduce our first speaker, Hal Evensen. I hope I got that right. It's correct there. It might be wrong in some of the other literature. He's a professor of engineering physics at UW-Platteville. He does some pretty amazing research on semiconducting carbon nanotubes. He looks at a lot of electronics and sensors, Internet of Things. He also, not just on research, but also Internet of Things education, engineering education. He has a project for virtual enclosures for grazing animals. He'll tell you all about it. Please help me welcome Hal.
All right. Yeah, thank you very much. So I'll be speaking on the work that I'm doing with a colleague who's here, Professor Cyrus Habibi from electrical engineering at our university, as well as Andy Cartmill from soil and crop science. And we've got a fabulous community partner as well, Chris Wilson, and I'll be talking more about him shortly. And so the title, that's the title of the grant proposal. It might be a little misleading because we're actually developing 2 systems. And so it's kind of a nice dovetail with the featured speaker that we just had. We are dealing with progressive grazing, and we're trying to not only help enforce progressive grazing, but also to monitor a dairy herd and pasture. And so that's kind of a little overview of where I'll be going with this here, a little background and motivation, and talking about both of the tracks that we've got and where we are and where we'll be heading next with this. And so there's our partner, Chris Wilson. He's a dairy farmer in Cuba City, Wisconsin, which is just south of Platteville. And as you see, about 500 head on 200 acres. And he's an organic farm, and he's been implementing rotational grazing. And so just to kind of spell it out, right, he basically pens in his cattle in essentially a 2 to 3 acre paddock. And then that little paddock gets advanced as they graze. So in the spring, he's moving it a couple of times a day. In the summer, not so much, right? His estimate is that the land is about 3 to 4 times more productive, right? Kind of as we saw with the keynote speaker. He estimates that the savings or the value for this system is about $100 per head per year. Just a little bit of his current flow then, you know, in the morning, he'll throw the doors open on the barn. And the herd will then kind of, if they're interested, right, they'll leave the barn, they'll head down the path, and then they're kind of guided into the paddock. They're not really led there. They're allowed to go there. They're chased off at the end of the day. There's always some stragglers. And they're not really tracked. So he doesn't necessarily know who's been there or how long they've been there. And so that's kind of his existing system. And Let's see, sorry about that. And so he's looking for some improvements in this, both in the time spent and the quality and the data. And so, like I said, the fencing is moved manually, and he estimates it's about an hour a day. Someone has to schlep out there, move the fencing, and then come back, or more than once a day. He's currently using a commercial tumble wheel system, which I've got some photos of, because as you'll see, we're actually building on this. It's, his estimate is about $10 a head a year in hardware, and so it's kind of this 6-wheel spoke. It's this nice ingenious design so that the 3 spokes touching the ground, or 2 spokes are not actually conducting to the ground, and then running through the center you can barely make out, but you can see is the electrified line. And so literally what he's doing in this video still is he's dragging it across along the edge of the field, right? He's got his permanent fencing on the edge, he drags that forward and advances it. And so there's the manpower and the time involved. Quality control, and by quality control, right, the reality is he's got employees. They may or may not all be trained up on the system. It may be a busy day at the farm and they don't have time to do this, right? And so some days it doesn't happen even though they'd like it to. And then there's this opportunity, right? He doesn't have much information on what the herd is doing, you know, which cows are feeding in the field. So there's an opportunity there for some data. So our goal then for overall here is a cost-effective means to support rotational grazing at this smaller scale, right, at the scale that he's at, 500 head. So our target is on the order of $10 per head per year. We could go a little more than that if we're able to get some value, some actionable data, right, on the herd that we don't really have yet. And just a little bit of background, right? We're not inventing anything that's never been done, right? There are systems that have full satellite tracking. For instance, large beef herds in Australia or Texas. Those can be rather pricey, okay, because you've got direct satellite communication back and forth with the cattle. At the smaller scale, still primarily beef herds, you can combine GPS with cellular systems to try to fence in or track your cattle. But yeah, it's still on the order of 35 a head a year. And so our question is, can we scale this system down to kind of the smaller scale? You know, and what we're looking at though is a couple of approaches here. The physical barrier approach, okay, some automated way to have a physical barrier, and then kind of a local collar system, kind of a smaller network that might be more manageable at the small scale. And so, like I said, we've got 2 designs that we're pursuing. I just call them the physical and the virtual. And so the virtual one that I'll talk about first, that Professor Habibi has been leading, is the cow collars with an invisible fence, right? Think of like the dog collars that we have with the invisible fence, kind of extending that idea. And then an automated mobile barrier, which I've been taking the lead on. There's some common features here. In both cases, right, we don't need the confinement to be perfect. Okay, there's permanent fencing that's keeping the cows from going over the cliff. The purpose of our confinement is to help guide them within the paddocks to help enforce this rotational grazing. It's not at the end of the world if one of them slips through. Okay, and we're going to work within the existing fencing. And then the system goals, right? It's out on the farm, so it needs to be something that's durable, hopefully simple, so it's easier to implement and maintain, and provides value. And we've got these 2 tracks because, honest to goodness, to me it's not obvious which of those is going to win. Okay, if price is no object, I know which one is going to win, but it's not obvious. So we're kind of pursuing these 2 tracks. And so to start off with, this virtual fencing idea is kind of a fun one. The concept is that the user would draw a paddock map using an online interface. And so this is a paddock around Professor Habibi's house, okay? And the idea is then that these coordinates are pushed to a smart collar that every cow in the herd is wearing. It gives it the coordinates, and it's going to be done over some local network. And then the collars are going to do their job of alerting or dissuading the individual animal from crossing the barrier. And so the idea is it offers flexibility. Right? You could put fencing up in any kind of terrain, around trees, around creeks, things like that. So it's got that promise of flexibility. It's also, if every animal's wearing a collar, you've got the option now of collecting data, information on every animal. Where are they? What are they doing? The physical implementation is rather light, right? It's a collar. You're going to have some networking hardware in the field or around, but And then the other piece that's there, as I alluded to earlier, is we can build upon prior art, right? This is something that has been in beef herds, perhaps on a larger scale, but there is, literature and background there that we can draw from. So some of the challenges are, right, these collars, there's a lot of electronics and hardware in there. And so that complexity is going to come with a cost. We've got this kind of $10 a head per year kind of level that we're nominally hitting. So that's going to be a challenge. And then this issue of herd acceptance, to me, will be something that we're going to have to test out. These rotational grazing boundaries are things that the animals are going to see multiple times a day, right? Unlike the beef herd that maybe randomly bumps into it every now and then, this paddock is changing on a daily basis, and they can't see it. There's no visual cue, and we know that the herds are used to visual cues. They don't bump into the electric fence every day. So how are they going to react to that? Is the audio cue good enough? We're going to have to find out. And so this is being developed, as I said, with Professor Habibi, with some student researchers that he's been working with. And so just kind of a picture of kind of what's in progress here is he's got this nice compact box design. It's powered by a solar panel that's charging a rechargeable battery. So that's kind of the bane of all of these things, is the power. They've got now, it's amazing, these cheap little $10 GPS units that'll get you within 2.5 meters. And again, for our goal of tracking where the cattle are, that's perfectly adequate. We've got an audio amplifier that's going to provide the first warning. So when it gets to within close to the border, there's going to be a sound that the cows can train on. This has been shown with other systems that the cows will react to that. And then, of course, at the end, you'll have a little shock module that would kind of be the final one. Ideally, they do that once. And at that point, after a training, it's really the sound that's going to get them to stay away from the barrier. And so kind of the flow here is that, again, you can set the boundaries, anything that gets you on the internet. So your phone, your iPad, your laptop, what have you. And then that boundary information is sent to these smart collars. In our case, it's going to be through Wi-Fi. This is something that we kind of wrestled with for a while. Our partner, he loves the technology, and he's figured out that actually it's not too costly to actually beam Wi-Fi into the field. So that's what we're trying right now. We're going to save energy and data by not constantly tracking the cattle. All right, we're going to beam the coordinates out, and then the collars are on their own. So that limit in information transfer is going to help reduce energy consumption. And then we're going to have automatic shutdown at night or in the barn. Right at the end of the day, they head back to their barn, and the collars are going to shut down and save energy. The other side of the thing is, the collars are going to be picking up a signal from GPS, but there's no transmitting up to a global satellite network. So by drawing information, again, that's going to keep the energy consumption down. One thing we are going to be looking into is kind of an advanced communication protocol, essentially Bluetooth hopping. This might be a way for us to transmit the information locally around the field without relying on Wi-Fi. So we're starting with the Wi-Fi, but this is something that we're kind of looking at on the side. It is kind of be an innovative way to move forward. And so we do have a collar design that's coming together. This is a photo from the literature. But what we're working on is something that's going to be smooth and durable polyester, comfort and outdoor use, and then it'll have a little halter to help kind of secure it on the animal. And so this spring, it'll be when we kind of assemble and test this virtual fencing. The goal is to have a full prototype by the end of March, and begin actually testing it in April and May. This image is nice because you can kind of see all the components that magically fit in or around that box. The GPS unit, our audio amplifier, our battery, and our speaker, and of course the solar panel. So that's the virtual side of what we're trying to do here. Okay. On the other side, and this is the side that I'm taking the lead with, is the physical fencing system. And so the idea is that there's these barriers. We want to automatically advance barriers somehow. We're going to begin here with semi-automation, meaning that somebody will be there to help make this advance, but then the end goal, our partner has made very clear, is that he would like to have some full automation. Again, that helps with the quality control issue. If it's a busy day, it would still happen. And so, it offers simplicity, right? Who can't just picture a fence that gets moved, right? Low cost and familiarity. Some of the advantages are that if you're able to move this wire that they're used to seeing anyway, that's more familiar to the herd, right? It's a visual cue, and moving it could be made compatible with the existing workflow, right? Right now, they're going out to the field to move these fences to check on the herd. If this can be combined with that practice, that fits in. Of course, if you've got a large mechanical system, we're covering whatever, it was 200 acres, 2 or 3 acres at a time. That's a fairly large-scale physical system. And so there's a mechanical durability issue if we're going to be building rails or any support structures, right? The size quickly gets out of hand. So we have this large area combined. And then, of course, cost is going to factor, right? The same cost-constrained supply to this side. And so the approach that we've taken on this side is I've been working with a series of senior design teams. We've got a College of Engineering, the capstone course, Senior Design, and so I'm working now with our 4th senior design team as we've been advancing chunks of the project forward. And so we've been basically progressing toward an automated concept. And so we started with senior design in fall 2020, and it was a blank slate at that point. In the summer, some students and I had come up with some design concepts, but we basically presented it to the students as we want to be able to automate this progressive grazing, full stop, right? If you're going to put poles in the field or have rails or what. And what they came up with, I thought was ingenious, is they just said, well, you know what? He's going out there every day to check on the herd anyway with an ATV, so let's make it so that he can tow the tumble wheel system with the ATV, right? We're using the existing system that's pretty minimalist, frankly, with all the hardware already. And we add a winch so that instead of him winding it up by hand, you push a button and it reels in with a little remote control, okay? The nice thing that I liked about this, right, is that there was no large-scale installations needed beyond what's there already, right? We're just automating the advancing of that tumble wheel fence anyway. And then the Internet of Things part of me, what I liked was that, well, this cart is essentially going to be parked at the entrance to the paddock, right? The gate is open, the animals walk in, and so we can make that a platform for a sensors suite. And so, for instance, we slap little RFID tags on all of the cows' tags. We know exactly which animal enters the paddock and which one leaves and when that happened, right? So there's some nice opportunities there for data collection of having something parked there at their entry point. And so then that led to the spring. And so again, our partner made very clear he really wants automation. And so one of the goals then in the spring was, okay, let's take this closer to automation. And so that was the spring 2021 senior design. And it was kind of a neat little discovery that wheelchair motors, who knew? They're out there, you buy them, they're wheels, they're integrated with the gearbox. They move at walking speed. They're made to move human-sized loads. And if you're just basically trying to replicate walking, advancing a fence, it's perfect. They're cheap. And so we've got a system with 4 of these electric wheelchair motors. You can see this little antenna up here. What they went with was that the cart had its own Wi-Fi hub. And so you'd put your phone on the hub, you'd fire up the app, or give the students an excuse to make an app, and basically you can drive the cart forwards, backwards, right and left. And so the hardware, it's not especially glamorous, right? Because in a certain sense, it's let's see if we can make this work. It's a Raspberry Pi. For those who are familiar with the electronics, it's about a $25 computer. And some integrated motor controllers. This was able to go through the field. This is also a video still. It was able to drag the tumble wheels, no problem. You can go over the unevenness and through the long grass. Kind of the next steps for this then would be to pair the other cart at the other end of the field, right? This is a single cart. They need to communicate with each other, so that's coming down the pike. And then also adding GPS. We would want to be able to get locations on the cart position. I had another team working concurrently on this, and they were working on a sensor suite. And so our partner wanted some pasture data, right? Temperature, pressure, humidity, that kind of thing. And then also some cart data like location, some inter-cart communications. They kind of weren't able to crack that nut. Well, at least they learned that what they tried didn't work, so we had to try something else. It's a sensor to measure the tension in the line that we're reeling in. monitoring that it's electrified, and then data storage. Okay. Of course, we've got this weatherized box. Things that would be coming in the future then would be this RFID that I'm still hot on. And then, like I said, we do need to come up with a better way to have communication between the carts. Okay. And so that brings us to kind of what we're working on now is really the last large technology piece that we haven't addressed, which is actually electrifying the entire cart, right? The whole thing's going to be brought up to hundreds of kilovolts, or numbers of kilovolts anyway. And so we're working on the automating the winch, right? So not somebody standing with a remote control, but hitting the go button, and it will reel it in until it's done reeling it in, right? So we have a sensor so we can get that tension right. And then the other piece is this little arm to raise and lower to connect to the fencing. Kind of a neat little realization from the design process. We had been using the same cheap GPS units that we discovered for the cow collars, but if you think about it, the cow collar had 2.5 meters plus or minus. You can't be 10 feet away from the fence and then try to find the fence, right? So we need a more expensive GPS unit, such is life. Yeah, so they're working on this winch mounted on a sliding platform. They've got a nice little design with a pressure sensor built in so they can kind of monitor that. So we'll be testing that here to try to get a sense of the force profile as it reels in the fence and advances it. And so these are kind of the last like unknowns really for the system. We're going to continue this into the spring. What's going on now, actually, I've got a student working with me. In fact, I just met with him yesterday. This thing is about as big as my hand, okay, my entire hand. And so it's a little smaller than it used to be. It's better weatherized, and it's expandable. So we've got a little expansion port on there. It's got the GPS antenna and as well as this communications antenna. RFID still on my radar. And the new thing is what happened over the past 6 months is that our partner committed to trying to get Wi-Fi into the field. And so now, right, instead of saving data to an SD card, we're going to be putting it up into the cloud so that he can access the data from anywhere. We do want a second cart. That's on my Git list for next semester, so we can try to coordinate the two carts. Once you've got plans for a cart, it's not senior design anymore, so I'll be looking for students that I can hire to just build the thing for me. But you know, the estimated cost, nominally, being conservative, meaning I'm going on the high side, about $1,400 in parts. The sensor suite, all in total, is on the order of $150. And then we had to upgrade from $10 to $300 for our GPS so that we get a better picture of where our cart is. And if you imagine, that's going to be key, because if we're going to automate this someday, we'll tell the cart to go to location A, right? And it'll be pre-programmed, and it'll go there, and we'll know it's there within a few centimeters, right? So that's well worth it. And so, yeah, so just in summary then, right, we're developing these two approaches to guiding and monitoring a herb that's in pasture. I've talked about both the virtual and physical approaches. You know, some commonalities, both are going to be giving us data on the herd. That's kind of the new piece. We're going to be using the cloud in both sense, this Internet of Things idea of I've got an interesting system, so I'm going to get data and put it where I can access it and analyze it. Both systems need local communications. So right now we're working on Wi-Fi, and as I mentioned, we're also considering kind of some advanced Bluetooth technologies that are out there as well that, again, work really well and really cheaply at this local scale that we're at. And so this spring is when we're looking to demonstrate some of those key components, such as the collar and that virtual confinement, and then also the electrification and the winch automation. So that's what I have for now. I thank you for your attention, and look forward to your questions afterwards. Thank you very much.
Thank you, Hal. Amazing technology, very exciting. Thanks. I'm Victor Cabrera, and I'm also serve in the Dairy Innovation Hub Steering Committee, and I'm also a dairy management specialist and professor in the Animal and Dairy Science Department at the University of Wisconsin-Madison. So now it's my pleasure to introduce the next speaker, and she is Iris Feng. I'm hoping I'm pronouncing well her name. and she's a postdoctoral researcher in the Department of Biological Systems Engineering at UW-Madison, working in Matt Dickman's lab, and she has expertise in methane emission analysis and predictive modeling of air quality and manure nutrients for both swine and dairy. Prior to coming to UW, Iris completed her PhD in agricultural and biological engineering at Purdue University. Please welcome Iris Feng.
Hi everyone, I'm Iris. I'm currently working in Dr. Larson and Dr. Dickman's lab and working on the manure sensing system. That will be the topic I will give today. So the first question is why we're interested in doing this. As we know, manure is a valuable agricultural waste that contains essential nutrients such as the nitrogen, phosphorus, and potassium that can fertilize crops and increase the soil fertility. But over-application of the manure fertilizer can lead to the nutrient loss to the environment and cause the groundwater and the surface water contaminations. So it is very critical for us to know the nutrient concentration in the manure and determine a proper application rate. So what people generally do, we collect manure samples prior to or during the application of the manure and send the samples to a certified lab for nutrient analysis. With the information of nutrient concentration, we can determine a proper application rates with some other information such as the agronomic needs and the available nutrient concentration in soil. Typically, we can also use the average nutrient data from some previous years, and this kind of nutrient management plan can help us to manage the application for years. So why we use a certified lab to do the chemical analysis? This is because the certified lab should follow the standard procedure of manure analysis proficiency program, and with this kind of standard, we can improve the precision, accuracy, and accountability in manure analysis. Although we can reduce the variability in manure application using this kind of control, such as the manure analysis proficiency and the nutrient management plan, there are still some uncertainties and the variabilities that can be introduced in the system during the manure sampling, manure analysis, soil sampling, and the soil analysis. So this kind of variability and uncertainty can also make the precise nutrient application very difficult to achieve. Another very obvious disadvantage is using the traditional laboratory chemical analysis, as this is a kind of expensive and time-consuming procedure. So what that means, this kind of time-consuming may result a time lag between the availability of manure nutrient data and the real application nutrient concentration when you're trying to apply it on farm. Because the nutrient in the manure keeps changing, during this time lag your analysis. So we're trying to find a way to solve this problem and improve the manure application accuracy. We believe there are two promising ways to do that with the help of the new technologies. The first one is where we can build an inline nutrient sensing system to provide more real-time manure composition data. And another one is we can use the variable rate application instead of the conventional fixed rate application to reduce the variability during the application. There are two sensors we will investigate in our project. The first one is a near-infrared sensor, and the second one will be a nuclear magnetic resonance sensor. Both of these two sensors have advantages over the traditional chemical analysis because they can provide rapid, high efficiency results, and they are non-destructive of samples. And also, using this kind of sensors, we can avoid the utilization of some hazard chemicals during the chemical analysis. There are many previous studies have investigated the application of NIR reflectance spectroscopy for manure analysis. The concentration the manure nutrient concentration they investigated, including total solid, like organic matter, nitrogen species, phosphorus, and potassium. And a few studies also investigated the application of using the NMR in manure analysis. But I think there is only one or two. And most of this previous analysis lab basis, so we want to expand this kind of lab analysis to some field application, you know. So the first study will be the accuracy and the precision investment of manure analysis predicted by the NMR sensor. So what we did, we collected 20 manure samples from 6 dairy farms in Wisconsin, including 1 UW research station and 5 local commercial farms. And parts of the samples sent to a certified lab I just mentioned for the chemical analysis of manure nutrients. And the rest of samples will be blended using a homogenizer to break the large particle size to less than 0.5 millimeter. Why we do this? This is because we want to provide acceptable sample viscosity for the further analysis used by the NMR. So this one this one is the NMR equipment we use in this analysis, and this can give the directly measurement of total solid, pH, ammonium nitrogen, total nitrogen, phosphorus, and potassium. And this equipment is pre-calibrated by the manufacturer. And another thing we're interested in is the runtime of the NMR, because the measuring process of the measuring precision of an NMR depends on the parameter and the measuring time. So that means theoretically we can increase the sensitivity or the precision of an analysis using NMR by just increasing the measuring time. However, we don't want to wait forever of analysis, because if it takes 2 days or 3 days more, we can get a R squared equal to 2 analysis, but that there will be no difference with the lab measurement though. So there still will be a time lag. So our objective is to shorten the waiting time and also get a relatively high accurate and precise results. So that's why we are interested in the relationship between the runtime and the NMR prediction accuracy and precision. For that, we conducted the measurement for total nitrogen and ammonium nitrogen and phosphorus at different runtimes. So this is the tube. This is a special designed tube for this equipment, and this is the surface of the NMR device. And the first thing we found is the NMR predictions were highly affected by the total solid levels. So why we found that? It's like, first of all, we plotted the results of NMR predictions versus the lab measurement, and we found 2 things. First of all, as the NMR prediction for total solid were overestimated. And then we found as the total solid increasing to about 8%, the fitness of the regression decreased. And then we plotted the residuals. We can also find another evidence of the difference with these 2 total solid groups. So as the total solid increased greater than 8%, the residual distributions of these two sample groups looks quite different. So to examine the total solid effect, we improve the measurement, we improve the analysis by assigning the samples into two different total solid groups, as one with the total solid under 8%, and the other group as the total solid sample, the sample total solid greater than 8%. And we found the NMR prediction were more accurate for the samples with total solid at a very low level compared to the high levels. So back to this, we did the same thing for the other manure nitrogens, and we found the similar results for the total nitrogen and ammonium nitrogen. So we can see the accuracy of the NMR predictions for total nitrogen and ammonium nitrogen were improved, was much better for the samples with total solid less than 8% than the total solid sample greater than 8%. But we didn't find the same. Results for the analysis of phosphorus. And the second thing we are interested in is the runtime rate. So here we can find the R square increase as we increase the runtime from 15 minutes to 60 minutes for total nitrogen and ammonium nitrogen. However, the increase is not that significant sometimes. That means there give us questions in future when we use this kind of equipment, if it is necessary to double the runtime by only increasing a 0.01 R square accuracy. And also we didn't find the runtime effect for phosphorus analysis too. So this is the example plot for total nitrogen, which is the similar thing as this. I will not talk that in detail. So there are some general conclusions from the first study. As the NMR predictions for total solid, ammonium nitrogen, and the nitrogen were more accurate for lower sample total solid, and but the total phosphorus was not affected by the total solid of samples. And another thing I want to emphasize here is, although we found the overall prediction of the total solid looks good because the R square is at a kind of a high level, however, when we further analysis the intersample and intersample variations, which the results are not shown here, we found that the phosphorus predictions using NMR was not that precise and robust compared to the nitrogen results. And also we found the accuracy and precision of NMR can be improved by running at a longer time, but it's not for all the parameters. For example, for the phosphorus, we didn't find it, Okay, so then we conducted our second study. We assessing the dairy manure constitute concentrations using the near-infrared spectroscopy. So the sample collection and the chemical analysis procedure is just as same as I described it for the NMR samples. But for this one, we're using an innovative spiking methodology to prepare the calibration sample sites. So what that means? That means instead of collecting more samples from the farm, we only collected 20 samples, and then we spike it in lab to create a large sample size for the calibration data. So we are using the lab chemical things, the ammonium chloride and the arginate as an addition to the samples to provide more concentrations of ammonium nitrogen and organic nitrogen. We spike each samples at 4 different levels, which is 1.25, 1.5, 2 times, and 4 times of the original nitrogen concentrations in manure samples. And finally, we got 100 samples in each spiking group. And we scanned the samples using an NIR spectrometer, which is this one, attached with a reflectance head sensor, so this one, and a transflectance probe, which is this one. For the transflectance probe, we can change the optical path length by changing this part. So you can choose different sensors with a different optical path length. So here we evaluate 3 different configurations of optical path length: 1 millimeter, 2 millimeter, and 5 millimeter. So after the data collection, we developed the NIR calibration models using the partial least square regression and perform that using the MATLAB. Several pre-processing has been evaluated for each calibration model, and the one with the best results would be selected for final decision. And we use the cross-validation method for calibration. And to evaluate the calibration models, we calculate the coefficient of determination, the R squares, the root mean square error, and the ratio of performance to deviation, as short for RPD. So these 2 figures showing the average spectrum of 100 spiking samples in 2 different spiking groups, using the 4 different sensor configurations. So the black one here is for the reflectance head sensor. The other 3 are transflectance probe with different optical path lengths. So what we found from these 2, we observe a reverse trend of absorbance and water peaks in the 2 different reflectance and transflectance modes. But we didn't find any difference between the ammonium nitrogen and organic nitrogen spiking groups. So here as the table summarizes the NIR calibration models for using all the 4 configurations. And what we found here is, first of all, we want to compare the transflectance with 3 different optical path lengths. And what we found is the transflectance probe with the shortest path length, the 1 millimeter, have the most accurate most accurate prediction for ammonium nitrogen and organic nitrogen, and for the total solid for both of these 2 spiking groups. Sometimes we observe the PB2, which is the 2 millimeter optical path length, works better than the PB1 for predicting ash and particle size. However, the difference between these 2 results were not significant. Actually, the prediction for ash and particle size using all these 3 configurations are just very similar. So we can conclude that the PB1, which is the 1 millimeter transflectance probe, had the best performance among these 3. So then we will use the PB1 as the transflectance probe and compare the results to the reflectance mode. So what we found here is we found the reflectance head sensor had better performance to predict ammonium nitrogen and organic nitrogen in both of these 2 spiking groups. And the transflectance probe have more accurate prediction for total solid, ash, and particle size in manure samples. So there are some main conclusions from this study. We found the shortest pathway works the best for transflectance to predict the manure nutrients. And we found that the reflectance can improve the calibration accuracy for nitrogen species. And the transflect mode works better for predict the total solid, ash, and particle size. So the main conclusion we draw here is the spiking strategy is a promising technique for a rapid and cost-effective analysis for dairy manure analysis using NIR spectroscopy. So what will be the potential benefit from our project? So first of all, it can reduce the overall system of variabilities by integrating this new sensing system to the existing, the application systems. But we need some further evaluation on that because as we didn't have like an overall picture of that. We haven't do the evaluation on that. And the improved accuracy and precision of the manure analysis can benefit to crop yields, and it can also reduce the supplemental nutrient applications such as inorganic fertilizers, and it can also prevent the environmental contaminations. And with the help of this new sensing system, we can develop a more detailed application map that can improve the nutrient management plans in future. Of course, there are still have some system limitations and unknowns of these new technologies. For example, the NIR system requires significant calibrations, and the prediction range is also restricted by the calibration dataset. And currently, we only evaluate the analysis using the liquid and the slurry manure. We haven't conducted the research on the solid manure yet. And of course, this kind of new technology may only be accurate for some constitutes. For example, the NMR, the data show like the prediction accuracy using NMR for phosphorus were not as good as the nitrogen. And also, we need to evaluate the overall system impact by integration this new technology to the existing system. I think I just mentioned this before. And also, in reality, we still need to do some traditional sampling, which is required for permitting and regulation purpose in many regions. So that means the widely application of this new technology may still take a long time to achieve. So some future work that we can do in the next step. For the NMR, we can do some recalibrations of the system using the specific manure samples, such as in Wisconsin, because currently the equipment of the NMR is pre-calibrated by the manufacturer, which is in Europe. That means they use the European manure samples to do the calibrations. This may introduce a lot of variabilities and uncertainty when we use their calibration model to analyze the manure samples in United States. And we need to investigate why the accuracy and precision of the total phosphorus prediction predicted by the NMR is not as good as the nitrogen species. And we also want to compare the NMR measurement to some other labs and other technologies to evaluate the NMR accuracy and precision. For the NIR, what we can do is we still need to improve the accuracy and precision of the calibration models before we can use it on farm. And we need to improve the procedure of speccing strategy in the manure analysis. Although the speccing strategy has been widely used for soil analysis, but I think our study is an innovative one for just use this kind of methodology in manure calibration model preparations. And we plan to develop a life cycle assessment and techno-economic assessment to assess the overall environmental impact and economic impact later. So this is another future work. We just finished a field trial last month. We integrated the NIR system into an applicator and use it to monitor the real-time nutrient concentrations in manure, and we use this to control the variable rate applications and compare that to fixed rate applications. And we will continue to work on this next year. Thank you very much.
All right, I want to announce or introduce our last speaker, Dr. Matthew Ruark. We work together at UW-Madison. He's also a member of the Madison Steering Committee for the Hub, so does lots of work. He's a professor in soil science. He's also an extension specialist, and he's affiliated with pretty much everything. I'm going to read some of these. UW Discovery Farms, the Center for Integrated Agricultural Systems, USDA Sustainable Dairy Project, Wisconsin Agribusiness Association, and Wisconsin Crop Management Conference. Basically, if you want to know something about cropping systems, he's the guy. So thank you, Matt. Let's give him a warm welcome.
I'm not sure about any of that, but thank you, everyone. So the title of my presentation, Water Quality, Nitrogen Use Efficiency, and Soil Health, the Shovel-Ready Projects of UW Discovery Farms. And this was a project funded by the Dairy Innovation Hub. So thank you for funding this project. So two things to start. What is Discovery Farms, and what makes some of our projects shovel-ready in the context of the Dairy Innovation Hub? First, I do want to acknowledge that all this data presented here is really is collaborative work conducted by Dr. Lee, who's a postdoc in my lab, Avi Augarden, who's a master's student, as well as Amber Raditz, Tim Raditz, and Eric Cooley, who are co-directors of Discovery Farms. So what is Discovery Farms for those that aren't familiar? So Discovery Farms is a farmer-led group that conducts research on farm and communicates results. That's the simplest way we put it. So when we talk about farmer leadership, we have 20 agricultural and environmental advisors that make up a steering committee. We meet several times a year to discuss our Discovery Farms projects. We conduct research on farm in terms of water quality, but also different projects, different survey-based projects that I'll talk about. And then we also communicate those results back to the farmers. So in this case, over the past year, we had 70 meetings with individual farmers to communicate back the results of water quality research projects, soil health projects, or nitrogen use efficiency projects. And then we also, we added up in terms of minutes because it sounds more impressive, but certainly we added up all of our presentations over the past year, came up in terms of extension and outreach presentations. So over almost 7,000 minutes worth of content was provided in different capacities, and we've written 47 articles that either go out in terms of on our blog, extension publications, peer-reviewed publications, and those sort of things. So we also historically had conducted a lot of field days. Perhaps some of you have been to a Discovery Farms field day where we can go out, look at these on-farm sites, see what's going on, talk about the results. So we do it out in a field setting, and then we have our annual conference as well, which will be in a couple weeks in Stevens Point. So the three projects that are shovel-ready are water quality, nitrogen use efficiency, and soil health. And so in the context of what I'll talk about today is what makes them shovel-ready is that the data already exists. So Discovery Farms has already had the investment in data collection in terms of water quality data collection, nitrogen use efficiency data collection, and soil health data collection. But we always like to joke we're data rich but analysis poor. And that's not to say we don't analyze our data, we do, but in terms of really diving deep into the data and working with it, that's what the Dairy Innovation Hub has provided funding for us to do. So as we go through each of these, so in terms of water quality, this is edge of field water quality monitoring to assess runoff and phosphorus losses from working farms in Wisconsin. For nitrogen use efficiency, this is on-farm assessment of nitrogen balances, very simple nitrogen balance assessment on farm fields in Wisconsin. I'll talk more about that, but we believe it could be a useful tool to drive some decision making. And soil health then is another on-farm assessment connected to biological indicators of soil health. Now, unfortunately, just in the context of time today, I'm going to focus primarily on water quality and nitrogen use efficiency. Perhaps I can come back in the future to talk about soil health. or you can have more conversations about that later. So I'm going to focus on water quality, excuse me, and nitrogen use efficiency. Okay, so for water quality, we collect edge of field surface runoff year round, right? So we work with farmers, we work with the USGS, we set up these flumes, things, water is collected on an individual event basis. And what makes it even more impressive is that we collect it year round. This is what makes our data set unique, where we're capturing the runoff, that's rainfall driven runoff, but also snowmelt runoff. And this is going to be really important because we're actually able to quantify the total losses on an annual basis. So there are many questions that we can ask with this data set. I'm going to focus on two ones here today. When are we at the greatest risk to lose phosphorus from our fields? And two, how do soil properties affect these phosphorus losses? And so, phosphorus is a key issue in terms of water quality, runoff, especially in the Lake Michigan watershed, where it can lead to some impairments in freshwater systems. So we want to work on reducing the amount of phosphorus that's leaving our field. Okay, so just a couple technical pieces here. First is I'm going to talk about components of phosphorus. I'm going to use the term total phosphorus, and that's just as it's the total amount of phosphorus that leaves the field. But that phosphorus can exist in two different forms. One is the dissolved phosphorus. That's just the phosphorus that exists in the water. It's dissolved in the water itself. And there's the particulate phosphorus. So this is what's attached to the sediment. So you have sediment-bound phosphorus, and you've got just the phosphorus that exists in the water. And those two combined will be the total phosphorus. I'm also going to talk about things in terms of load, and that's going to be the mass per area, so pounds per acre that physically leave the landscape. But the amount of load is often driven by the amount of runoff, so we will also use, we standardize it based on concentration. So as if we would collect all the runoff that left the field and get an estimate of the concentration of that phosphorus in the runoff. So we're going to see the concentration, sometimes it's going to be referred to as the flow-weighted mean concentration. So we always have to use slightly more complicated terms. That's how you know we're good scientists. Right. So load and concentration, dissolved phosphorus, total phosphorus. We're going to be going back and forth. So the first thing we talk. So the first question that I posed was, when are we at greatest risk? And our data set really revealed that 40% of our total phosphorus losses are occurring during frozen conditions, based on our data set. And so here's this is the relationship between total phosphorus loss and dissolved phosphorus loss during our frozen periods. So this is the summing of the frozen periods. And what was interesting is 80% of that phosphorus that's lost with snowmelt is in the dissolved form. So we're not losing a lot of total phosphorus or particulate phosphorus. We're not seeing a lot of erosion happening at that point in time. But in that case, it's really the amount of phosphorus that's in the water. So when we see this, when we have these snow melt events, that's a huge part of the phosphorus loss that's happening in our landscape. And more specifically, what's driving that, when are we at greatest risk? We're at the greatest risk when it comes to late winter manure applications. So late winter manure applications can increase phosphorus loss in snowmelt 2 to 4 times. So what we have here, this is the relationship again between total phosphorus loss, individual phosphorus loss. This is by site. And so this is the summing of over that frozen period. And you can see when we have these big phosphorus losses that are occurring, this is occurring with late winter application of manure, February and March, as opposed to no winter manure application or early winter application. So we have this example where when are we at greatest risk to lose phosphorus? During snowmelt, and it's exacerbated even more when manure is applied in February and March. Part of this other analysis is that we're able to sum up all of these things over parts of seasons, over an entire year, but we also can look at stuff on an individual event basis. And so the next level analysis that we have done here is we've got over 1,000 individual runoff events in our data set to explore. and I'm going to present it all in excruciating detail, right? So here we have the total, this is the total phosphorus versus the dissolved phosphorus, and what's interesting here, when we look at it on an event basis, we see very similar results, where we see that, again, we have this broken out into three components. In the green is when runoff events that were driven by rainfall during the non-frozen periods. The blue is runoff that occurs from snowmelt. And then we also have this third category of when it rains on frozen ground. We had a few of those in there as well. And so basically when we're losing phosphorus, or when there's runoff occurring during snowmelt or precipitation on frozen ground, we see that the amount of phosphorus is primarily exists as dissolved phosphorus. We're not losing a lot of sediment, it's primarily dissolved. However, it's a complete opposite effect during the growing season when we have runoff events that lose phosphorus. We see most of that phosphorus exists in the particulate form. So where we're seeing only about 13% of that total phosphorus is in the dissolved form, so 87%. Again, we are seeing dissolved phosphorus losses being greatest in the frozen concentrations, but also during large runoff events, they're made up almost entirely of dissolved phosphorus, or in the growing season, or entirely of particulate phosphorus. Meaning that we have different parts of the growing season, and we have completely different speciation of phosphorus we're losing at different times. So what about tying this individual event analysis back to the timing of manure application? Right, so what we have here is on the x-axis is days since manure application. So we went in, we coded, we assigned every individual runoff event to a day since manure application. So manure had been applied on most of these fields, and there would be so many days since manure had been applied when the runoff event occurred. And so on the top is the total phosphorus, so that's everything, and on the bottom here is the dissolved. And we do have it color-coded by snowmelt, non-frozen, and frozen precipitation events. So the first thing is that it is messy data. There's not a clear effect. Our supposition was that we would see a really clear effect, that the closer, if you put out manure and then you had a rainfall event that happened immediately after, those would be associated with the high rainfall events, or high phosphorus loss events. But what we see is a very subtle effect, only a slight effect, not very predictive in terms of our R-squared, in terms of a slight increase when rainfall happens shortly after a manure application. But what we have here is a wide range of phosphorus losses that can occur relative to every single manure application. So every rainfall event on an individual field is its own special event that has a lot of factors that go into place that would drive how much phosphorus is lost. For dissolved phosphorus, the other way to look at this is that we are seeing a lot of high loss events happen when rainfall happens close to manure application. So that does happen. But we can also have middle to low levels as well. So we can get the whole range that can occur. But what's also interesting with that is that we can also continue to see high phosphorus loss events happen up to 100 days after a manure application. So while manure application individually is having an immediate effect, there's also many other factors in play that can lead to high phosphorus losses. Now, in our analysis, we've pulled out the soil test phosphorus as the main factor. So what we have here is that with most of our dairy farms, we have manure application. We've had continual manure application over many years, decades. We see a buildup of soil test phosphorus, the phosphorus concentration in the soil. And so here's a simple analysis where on a site basis, this is the soil test phosphorus in part per million, and this is the annual flow weighted mean concentrations, and we see a really clean relationship with an R-squared of 0.89 with greater soil test phosphorus, the greater the phosphorus concentrations in the runoff will be. So what does this all mean then? So when are we at greatest risk? So during snow melt, when manure is applied in February and March, but also anytime there's high amounts of runoff in the soil, right? So we have anytime there's a lot of runoff, and that really ties into this aspect of, because we are working mostly in a lot of our dairy systems in soils with very high soil test phosphorus levels. So greater soil test phosphorus leading to greater phosphorus losses. So it's the combination of drawing down soil test phosphorus in conjunction with eliminating manure applications in that February to March that will help reduce those high loss events. I make this sound like it's simple, right? We have we have a lot of phosphorus we have to work with in our systems, and working to not only improve the timing of application, but also our phosphorus balances in ways that we need to reduce our phosphorus in our soil. And there's just no other way to get around that. I've lost track of my time, but nitrogen, how much time do I have? No idea. Okay. So, perfect. I have exactly 10 more minutes worth of content. That's amazing. So that's our runoff side. We have these big data sets, and we're working on exploring a lot of other things, and we're using a lot of multivariate analysis. And I could have shown a lot of really complex modeling and stuff like that. But really, it was really the message there is just the variation with those two main the variation in the amount of phosphorus loss with those two main factors kind of pulling out as important ones. So we have this other aspect of working on water quality as it relates to nitrogen, is this concept of nitrogen use efficiency. And when we talk about nitrogen, I talk about nitrogen use efficiency as a very vague term, and we've done two specific types of measurements on farm fields. One is something we call the partial factor productivity. This is a factor that every farmer could calculate for themselves. It would simply be the yield divided by the nitrogen applied. Then we also are working with something that's the partial nitrogen balance. That's the nitrogen applied minus the nitrogen removed. Excuse me. Where if we have a positive value, that would imply more nitrogen was applied than removed. But if you have a negative value, that would indicate more nitrogen was removed than applied. So in most of our grain production systems, we tend to see positive values. More nitrogen tends to be applied to our fields than what we remove. And that has some nitrogen management implications and has some water quality implications. So I'm sure everyone's seen figures that look like this. This is really what drives a lot of this. The need for these types of measurements is that we do have a lot of nitrogen in our nitrate in our groundwater, and we don't have a really good tool to help farmers really visualize, how much nitrogen they may be contributing to groundwater. So our overall premise is that farmers need to see their nitrogen as measurements of nitrogen use efficiency to help with decision making. Excuse me. So if there may be a nitrogen recommendation, but at the end of the day, how much nitrogen, what's your nitrogen balance on your field? And so if farmers had a better sense of where they ranked relative to their peers, that would provide evidence that changes to their nitrogen management would be beneficial. Now, we're not saying we don't know exactly what specific management practices may be beneficial, but if a farmer knew that they were on the low end of nitrogen use efficiency measurements in their area, that would be a piece of information they could use to say, okay, there might be something I can do it might be worthwhile to change something I'm doing in terms of nitrogen. So we've set out, this was our previous work, is that we set out to benchmark these nitrogen use efficiency metrics for corn grain and for corn silage, and we already have a publication that benchmarks them. So farmers could calculate this for their own fields, compare to where they are on these statewide benchmarks, and then use that to say, oh, I'm pretty efficient. Maybe there's some minor tweaks to be made, or wow, I'm really at the low end. I really need to think about my nitrogen management decision making. But what we're interested too is like what are the drivers? We conducted this work on over 200 corn grain fields, about 100 corn silage fields, and we want to understand, well, what were the drivers? Could we pull out anything in this data set in terms of what are the drivers of high use efficiency? Was there something in the data set we could extract to identify it's this set of management practices that are going to lead to greater efficiency? So the calculations themselves are simply based off of yield and the amount of N applied. Pretty simplistic. So which one of those are going to drive it? So when I'm going to use corn silage as an example, and this is the partial factor productivity, that's the yield per N applied. This is the nitrogen balance, where it's the N applied minus N removed. Where we see, what about the yield? And the yield really is having a relatively small impact on the overall efficiency, where we can get a whole range of yields being produced at a whole range of efficiencies. So just simply increasing yield would certainly take up more nitrogen, but in our data set did not say that that was a big driving factor for efficient use of nitrogen. On the other hand, when we look at the amount of N applied, that was the main driver, where it explained about 60% of the partial factor productivity, 56% of the nitrogen balance. So across all of these approaches, it's on the landscape, it is still the total amount of N that we're applying that it's affecting the nitrogen use efficiency. I'll also say this, we used a nutrient management based approach to this, so this is not the absolute total amount of nitrogen applied. So when we did, based on manure nitrogen applications, we're using the available nitrogen, not the total nitrogen. So what does this mean? So looking at even just a pare down or just a partial subset of our data, when we ranked our fields from the lowest efficiency on the left to the highest efficiency on the right, we graphed up the total amount of N they applied. And we also graphed it by source. So that implying then the amount so in this first one we had over 400 pounds of nitrogen applied. And that did produce our lowest efficiency. But in the brown is our manure nitrogen that was applied. In the gray is the fertilizer nitrogen applied, and the green is the legume, which is typically the alfalfa nitrogen credit. So if you're following alfalfa. So a very simplistic approach to looking at this is that in our low nitrogen use efficiency, I don't know what I did there. Maybe I'm not doing it.
You're taking something.
All right. So anyway, so our lowest efficiency comes with when we're putting out a lot of manure nitrogen, and what this comes down to is that there's still a lot of fields on the landscape, unfortunately, that aren't crediting their manure or aren't crediting the nitrogen in the alfalfa, and they're continuing to apply extra fertilizer, and these sites that likely didn't need them to begin with. So it may not it's not necessarily they're applying too much inorganic nitrogen. They end up doing it, but in a way because they're not assigning value to the fertilizer or to the manure nitrogen. So we conducted it with this kind of data set, all of these multivariate approaches, and we factored in tillage, we factored in clay content, we factored in drainage class, we factored in all of these variables. And at the end of the day, it was still the total amount of N applied is driving our use efficiency on our landscape. I really don't know what's going on here. So this, we have a lot of investment in. I don't know if I'm doing something here, but I think I'm rocking the. Yeah, don't move. Okay, so I would say we have a lot of investment in nutrient management planning. I think that there's still a tremendous amount of work that could still be done. We need to credit the manure, nitrogen, and alfalfa as nitrogen sources. We do feel that these calculations for nitrogen use efficiency can be important for farmers when deciding they should change their nitrogen management approach. This was very eye-opening to all the farmers we worked with. But the idea of nitrogen balances, especially in corn silage fields, are not going to be necessarily helpful for assessing the impact of groundwater. And I don't know if anyone caught this, is that when we're looking at the nitrogen balance on these corn silage fields, we have a lot of negative values. So it would imply that we're removing more nitrogen than we're applying. But that's not, we're not leaching negative amounts to groundwater. So there are going to be usually corn silage is going to come with some manure application. We are going to have some nitrate leaching. So unfortunately, I think it's a good assessment tool, but probably not not going to be a valuable tool or not going to be a useful tool when understanding the impact to groundwater directly. We need field-based work with actual quantifications of measurements to do that. So where does this leave us? In terms of nitrogen leaching and runoff, we need to push innovation in nutrient management and conservation management in our cropping systems. So we just simply have, we have some farm fields that aren't leaching much and aren't losing much phosphorus, but we do have some that are leaching a lot. We have a whole range of things that are happening. We have the whole range of things that are happening in our landscape. And these were farm fields that let us go on their field and measure the things. We need more quantification of leaching losses of nitrogen through rapid, inexpensive sensors. We need more quantification. So it's just simple nitrogen budgeting isn't going to get us to where, isn't going to get us those assessments of nitrate leaching and really knowing that impact to groundwater. So we need that. And I think then at the end, I think we should ask the question, how far can we push productivity in our dairy and cropping system? Certainly, we can talk about corn and alfalfa yields, but what about also winter silage yields? How do we, if we're putting out these many nutrients on the landscape, how do we capture more of them in an effective way? And is it possible? So can we actually push the system, can we push the system more? And perhaps there's ways to do that, especially in corn silage-based system, and especially if we are going to have manure be applied in the fall. So I think this was, we really appreciate the funding from the Dairy Innovation Hub, and we will continue to keep working with these data sets over the next year. So thank you.
You guys can make the slide. So we're going to start the question and answer session. If I could get all three speakers, Hal, Matt, and Iris, to come up here. And what we'll do, if you just raise your hand, so if you guys want to come up here and, I don't know if we can grab another chair. You guys want to sit at the panel. What we're going to do is if you raise your hand in the audience, if I can get this microphone here, I'll bring the microphone to you. And those online, if you have some questions in, we can have those read off as well.
Test 1, 2. That one should work for panelists if you want to get it quick.
So do we have a microphone?
I'm trying to get it to work. That's what's happening.
So maybe we can start. Maybe I'll just ask the first question until we get the microphones going. So I noticed there's an awful lot of data on manure and animal units, animals moving around the landscape. Who's going to own all this data? And I realize that's not what your talk was about, but I'm just sort of something all three of you have an awful lot of data. Farms are suddenly becoming this rich source of data. Interested in your opinions on, as this data is generated, who's going to own it? Is it all going to be on Amazon servers? So I don't know who wants to take that one first, or if it's even a fair question, but very interested in what happens to all the data and who gets to own it and use it.
I guess I'll jump in first. Yeah, because we're talking about collecting data on the herd and things like that, and the hope would be that it's the Wild West right now. Okay, the hope would be that the farmer, the herd owner, that it's his data. He would determine how it gets used. The reality is, of course, we'd be paying the man at Amazon for storing the data or wherever to access it. But in a sense, you're renting or using their server space. And so, it's not so much that they have, okay, they do have control of the data in the sense that it's, their server, but it's not necessarily that they're collecting it or filtering it or things like that. So, yeah, I mean, in our mindset moving forward, the data is going to be owned by by our partner, by the farmer, and he would get to decide, how that data is used or distributed. Yeah.
Actually, I agree to the opinions, Dr. I'm sorry. The one more thing I can say here is like when I collected data from like local farms, there are some farmers that they're really interested in the data we collected, and they want to get some feedback from our research. Even though I don't know after they review the data how they want to do with the data, but I think some of the farmers are really interested and they want to use the data from the research studies to help them to improve their productivities or management.
And then for the Discovery Farms data, right now all the data is available upon request. But eventually what we're going to see is we are going to take these and put them into data publications. There's a lot of resources like that. Also, a lot of publications are asking for data sets to be published with the data. So when it comes to the type of data that we generate in academia, those things eventually should be publicly available and are available upon request. But eventually we have to get a better system of getting that, getting these things streamlined and getting data sets published, because then they can exist and other people can work with the data and explore new things. Maybe some economists even.
All right, so do we have the other microphone?
It's not working, but I can pass the microphone if there are questions in the room. Nikki will provide some
Check
questions.
1, 2, check, check, check.
All right, but they need a microphone too, Victor, so, yep, no, so are there questions in the room? Oh, it looks like we have a microphone actually working. This is good now? So are there questions in the room? Yes, let me just ring it around. If you could just state who you are too, that'd be great.
I'm Veronica Justin from UW-River Falls, and so my question is for Matt. Actually, I have two. One is we know that corn varieties have been bred to try to have increased nitrogen use efficiency, so I'm not sure if, how long your data set goes back, or if there's any portions of your studies that kind of divide out what we might think the role that genetics might play in nitrogen use efficiency and changing those kind of models. And then my second question is if you could just elaborate on kind of what maybe you are looking at in terms of soil health for your initiatives at the Discovery Farms.
So our nitrogen use efficiency assessment was over the past 4 years, so recent genetics. There's several publications that have shown that increased use efficiency of nutrients and uptake over time with hybrids over time. The problem is the end inputs at the landscape level get messy, and it kind of ties into this precision manure will have a help, certainly, if we can fine tune the exact amount known to be applied. So that's really exciting. The problem is we still have this big variation in the amount of N applied that's actually available. So we have these recommendations of available N, plant available N from manure, and it's maybe 30 to 50% of the total nitrogen manure. So the question is, first is, there's an error bar on that. We don't report it, right? We talk about nutrient management plans like it's absolute, but there's, sometimes it could be as low as 10, sometimes it could be 80, and there's a lot of things that go into that variation. So really in terms of the nitrogen use efficiency here, it's really the manure that's driving a lot of the complexity, not necessarily the genetics. The second part was, soil health. So what we're interested in was to benchmark some of these biological measurements of soil health. So we have a lot of, most of our soil testing is built around soil chemistry, but we know that soil biology is really important in terms of nutrient cycling, building organic matter, and those sort of things. So we've been conducting a lot of these simple biological tests that might be useful, that could be used by soil test labs. And so we're evaluating, one, are they sensitive to changes in management, and also how are they connected to inherent soil properties and stuff like that. It's another half-hour presentation, but it's some exciting things we're finding. So, and some potential useful measurements.
Other questions? Mitch?
I have two. I'll put them together. So like building on that, BMR corn silage tends to have better productivity on the cow level for digestibility. However, it has a yield drag to it. So if you, fertilize BMR corn silage to the effect that you're fertilizing a different hybrid, there's potential for a lot poorer nitrogen efficiency, I would think. I can't say that that's true, but I would think that that's very interesting. And then my second question is based on your manure thing, and I probably should know the answer to this, but I'm going to ask it. So what % of manure nitrogen over the life of that manure is used by the plant? So 50% in year one, but over 7 years is 80%, 60%. I don't know the answer, and it's very intriguing to me.
I'll answer the second part first. So we did not include, we estimated the available N based on the way the farmer was applying it. So how they apply it affects the availability. Typically we talk about 10% of that N is applied in a second year and even maybe 5% in a third year. But so in most cases, especially if it's a surface applied manure, certainly less than 50% of that total N is going to be utilized by the crop, for lack of a better term. Or have that sort of fertilizer equivalent value. So as we go into some of these other silage-based systems and different, the hybrids and the brown midrib, I don't, and those are a lot of things that probably are, at least, I don't know if we have, I'm sure we have some data somewhere, but like in terms of how much N uptake, what's the efficiency, and also if we're looking towards the quality components. And a lot of times too is like in our fertilizer recommendations structure, we provide a range of in terms of a nitrogen application that would maximize the return on the economic return to the nitrogen applied for corn grain. And then we just quite simply say, well, apply towards the top end of that range for corn silage, presuming that it's going to be pretty expensive to buy it off farm and you want to try to capture it. So there's a lot of economic things in there, a lot of economic reasoning for why we might be on the high side for applying nitrogen to silage as well. So there's probably still a lot to do with kind of fine tuning those things. It's a tricky one for sure.
I'm Emily Volker. I'm a student from River Falls, and I have a question for Hal. So you mentioned that in using those collars that you use Wi-Fi. Have you thought about using satellites with GPS or not? And like, why did you choose Wi-Fi?
Sure. Yeah. So the reason we decided to go with Wi-Fi as opposed to the satellites with GPS is that the satellites with GPS are kind of in some of the existing systems that are really used for really far-flung herds, like beef herds and large ranges. And there's an expense there, and it's an expense two ways. One is you're tying into this satellite network, and it could be two-way communication, which is even more expensive. And so there's a money aspect, but there's also an energy aspect. Beaming the signal up into that network requires a lot of battery power. And for any of these electronics that you're putting on the herd, that you're turning loose in the field, the battery life is a big deal, right? We don't really want to be changing the batteries too frequently. And so Wi-Fi is essentially a lower energy method for us to get the information distributed. And so that's kind of one of the features. Like, these things are out there. They're products. You can buy them for your herds if you're kind of this large-scale beef farm. But if you're kind of a smaller-scale dairy farm, then the question is, where can we cut back on these things that are expensive, both in terms of cost and in terms of energy? And can we cut that back enough to kind of put it in the price point where it's useful for kind of the smaller scale farmer? So yeah, so good question. We did consider it as part of our background work. And so that's why I say Wi-Fi now, because it's easy and it's available. And it turned out to be surprisingly easy to beam that into the field. But then we are looking at next generation stuff like the Bluetooth hopping, which is even lower energy. It's a newer technology. But it would enable us to kind of use the animals themselves. The signal could hop from animal to animal at a fairly low energy. We're used to Bluetooth for our headphones and things like that with its 10-foot range, but the advanced technologies get up to about 300 to 500 feet. And so that gives us some more opportunities there.
I had a question for the second presenter. I think the very last slide, was that the technology that's using for the variable rate applications? If you could go into a bit more detail on what's planned in terms of looking at those variable rate applicators, what are some, if you have been utilizing those, what are some issues that you're seeing versus what are some real benefits of that potential application?
Yeah, sure. We just finished a field trial to using that technology. So the picture showed the yellow box, if you still remember that. That is the NIR sensing system, which including the NIR sensors inside it. And we also installed a flow meter attached with that. And that is connected with the applicator. And we can get the real-time manure nutrient data from the screen in the control room. And you can read it, and you can set up a target rate, or you can target a fixed nitrogen application, or you can target a fixed rate. So we can adjust it during the application. So our plan is to analyze 3 different variable rate versus 1 fixed rate applications. So we will target 3 different levels using variable rate application and compare that results to the fixed rate. But currently we only finished a pilot kind of trial because we want to investigate if the system can work, as we expected. We collected manure samples during the application, and we send the samples to the certified lab, and we are still waiting for the results from them. We're trying to compare our target rate and the real application rate from the applicator, and compare if the system of the NIR can control the application accurately. So, if I answer.
My question is for Matt. You mentioned using of nitrogen measurement using inexpensive rapid sensors. Is something that we need to develop or is already out there available?
So both, right? I think that there are some that are out there and we need to continue to develop. So for those that listened yesterday, so Dr. Jinghee Wang is working on some sensors. But quantifying nitrate, we've done a lot of work in quantifying surface level losses, and it's a lot of work, but we've got a fantastic data set with it. But we really don't have that much data that's quantified nitrate leaching in the state. It's much more. We're working on smaller scales because we can do field level capture, but when we're doing actual leaching, maybe even if we're using a pan lysimeter that's maybe 3 feet by 1 feet, that's still not that big of an area that we're collecting under. In any case, we need to ramp up that, and so I'm really interested in the work that Jinghee Wang is doing. I think that all the engineers should be turned loose on trying to develop these sensors because we don't have anything yet. So, yeah, that's good.
Other questions from the audience? Well,
Sorry, I was going to ask Lily a question. And actually on the topic of sensors. Yeah, because I'm interested in sensors and measurement. And one thing that struck me was that there was a lot of scatter in your data. And you kind of said, and I agree, in general you want more precision and accuracy so that we can, and as I understand it, right, so that we can have better control over how we fertilize the fields. And I guess my question is, how much precision and accuracy, right? Because I get the impression that there's a wide range of scatter in the data, right? And so I'm wondering, are you talking 10% or 1%? Right? What would be a good, actionable precision, accuracy that would allow you to have that, the advantage of the good control? Because at the beginning of your talk, and you addressed it in like the next slide, I was thinking, how much, there's got to be how much variability is there from a cow in Wausau to a cow in Grant County, right? And apparently there is. There's enough that it affects the quality of that, of the manure dispersal. So I'm just curious as to, you've got this goal of better precision and accuracy, and what level would be good enough to actually have some improvement?
Thank you for the question. So that's also interesting. Actually, honestly, I didn't think about that before you asked me that questions. Because for me, I think like a little bit improvement can help us, But another thing I want to emphasize is, besides the increasing the accuracy, the other thing we do this is we want to get a real-time data. I think that is more important things compared to the how much accuracy we actually improve, because the time lag between the availability of the nutrient data and the real application nutrient concentrations on field, that is a big questions in this system, because if you're waiting like a half a month to waiting for the laboratory analysis before you applicate the manure on field, the manure keep changing during this half month, and when you apply it on farm, it's not the actual same manure as you analyze. So that will be cause the most variabilities, for my opinion. So you want to answer the question, Dr. Larson?
Yeah. No, Iris, you're doing great. I just wanted to talk a little bit. I'm Becky Larson. I'm working with Iris. We've been working on this project, and we've got a lot farther to go. So I would say she's been working in the laboratory. It's hard to put a number on how well it's going to perform. That's why we have to finish these additional trials. I think, to me, if this additional, so there's variable rate where you can control the rate, and then there's this additional thing where we're trying to see how well we control the actual nutrient application. So there's some variability in the NIR system compared to maybe what we traditionally use. There's also some variability in the flow meter. There's also some variability in the application system. And so I think what we've been looking at is, if you can't really see a difference in either crop yield or larger scale impacts, or you can't see differences in environmental impacts, which we're going to take the data from the larger trials and try to put those into LCA, or we're not going to see economic impacts, that maybe these kinds of interventions are not very effective. Or at least from that data, we'll be able to say, if you can't improve the accuracy of the NIR by such and such %, then we're never going to hit a point where any of those are impacted. So I think, to me, trying to pick like a number just isn't that effective, and why it's kind of hard. I feel for Iris having to present this data where people are like, what is that doing? Because we're really just getting to the point of how do we use this to make any differences. But I would encourage any other thoughts that people have.
All right. Last call for questions.
I can ask from here.
Yep.
Sure. Maybe this would be a question for all our speakers this morning, and follow up somehow on Troy's question about the data. But I would like to touch on how you can leverage those data. I mean, the 3 projects are developing or creating data, or using available data, and also producing data through the projects. And I mean, I like the idea in Hal's project that has a target price for the development of the product, right? So that's important to make sure that's going to be adopted and used in the industry. But another way to see it is how we can leverage those data connected with other data on the farm to produce value. So I don't know if you have thought about that, or what would be your thinking on how you can use the data you are using at the moment or creating at the moment with other devices on the farm to produce more value. You want to start, Hal?
Stalling. Yeah, because what you start with, and what we're starting with, is right. We're using our partner's knowledge. So Chris suggested to us, here's the sensors that I think are going to be the most important, the most relevant to, at the end of the day, the goal is improved production. right? And so, we're collecting the field data. He wants to know what the different cows are eating, right? He doesn't even know which ones are eating feed, which ones are in the field right now. And so, he kind of keyed in on, here's the data, the types of data that we want. And so that informed decision-making was key. But then the next part will be, right, we don't know what the answer is going to be. We just suspect that those are going to be important pieces of information to have. So then we're going to have to get a big pool of data, right, and then start the analysis later once you've got this big pool of data, right? So I'm jealous of the other two speakers who have data point after data point, right? They've got a lot of data and they can start the analysis and the mining. So we're not there yet. We're still in that design phase, and so that is an important thing. You don't want to collect data on just because you can, right? We're trying to make informed decisions of what sensors to stick on there, because that's kind of a pit that people can fall into in this age of big data, is just collecting everything and letting the computers sort out the mess. We really need informed decision making on what sensors to select, and so that was what guided our choices. And so the idea would be that once this is out in the field, Chris is going to have a season or 2 or 3 of data, and then would be able to kind of look at it and see what impact these various things had. Time spent in the field, we could probably link that to the production of an individual animal. These are the things that would be enabled by that.
Thanks.
I think yes. So data sometimes is powerful. Sometimes it's just a waste of time to collect more data. So I think it more depends on how you want to use it and how you analyze it. So for me, I think like what we use to build the model, the partial list of square regressions, that's a way we choose to analyzing the data. And we're trying to make the data useful rather than nothing. If I publish the data, like the raw data, nobody can understand it. So I think that's a way to how we help us to use the data is with the help of innovative methodologies, like especially in statistics. For example, I think why we collect the data and how we benefit to the farm is like we collect the manure data, we can use it to help us to improve the nutrient management plan. So as you keep collecting more data, then you will have like a more overview for such as the soil nutrient compositions and the Wisconsin manure nutrient compositions. Then if you added those data to improve the nutrient management plan for years, then you can get some feedback or outcomes from your collecting data. Yeah.
Thanks.
And from our end, it's really about what's next in terms of would our farmers going to be willing to contribute data to a public database? Because we did all of this work and we got 300 data points or things like that, but it was a lot of work to get 300 data points. To spend 4 more years to get another 300 data points isn't going to be worth it. We need 1,000 more data points. We need 10,000 more data points for use efficiency, but also all the management practices that go with it. So can we create some sort of citizen science approach where we can contribute this broad information and then use that to do even better, have a bigger data set to data mine to really figure out where efficiencies, what practices are going to lead to better efficiencies. We haven't figured out how to do that though yet.
Well, Randy's got a question, or do you have a comment? Do you have a comment you want to make with that question?
I had a question about the follow-up on the data thing, but
Actually, I think we're just about out of time. We have maybe one quick question from the virtual audience. Oh, no. We have 3 minutes. All right. So, Randy? All right. I thought that was a question.
Mine's really easy and short. It's 2 parts. It's for Matt, my friend. Matt, from all these data, is there a relationship between the amount of nitrogen applied and corn yield?
No.
That's fascinating.
That's interesting.
B, what fraction of the nitrogen applied, whether it's manure or inorganic or both, is lost to the environment?
I don't know.
How much is taken up by plants? That was a question earlier, right?
Right. So we're looking at, I don't know. So that leads, so your first question is, these are all working farms, and we're working under the premise that every farmer has trial and errored their way to their end application rate. But you can have high yields with moderate amounts of nitrogen. You can have high yields with high amounts of nitrogen. You can have low yields with low. Anyway, so it's all over the place. It's just a shotgun blast. There's no of what's happening in the landscape. There's no fundamental relationship between yield and N applied. But the reason why we don't know is because we don't know how much nitrogen is contributed from the soil. And so that's another part of this project. We have a lot of, we have farmers who have put out 0 nitrogen strips. And so we're looking at the nitrogen uptake with 0 nitrogen. So, but that's really the only way you would know, because we don't really know how much. If your soil's supplying a lot of nitrogen, then the amount of nitrogen you're applying as fertilizer is going to be less likely to be utilized. So that's the big caveat, plus texture, plus how much it rains that year. So that's what creates that variation. We don't know exactly how much is lost within that year. But within yeah. We'll just leave it at that. There's a lot more on-farm explorations. There's a lot more on-farm explorations, I think, that we could be promoting for farms. It's more work, but they could provide some value for decision making of how much actual N to apply and how much and how efficient you can be.
All right, I think we're actually at time, so I'm going to let Randy and Matt have that question outside they probably can do that at the union maybe at some point. So let's thank our 3 presenters, our 3 speakers one more time. Reminder, I think we're breaking for lunch, and then there is an afternoon session. Please stick around for the other 2 tracks. Thank you all.